Hello, and welcome to the incredible world of gesture control technology. GCT is a motion sensing and interpretation device that allows a person to actively interact with a computer, and not through typical mechanisms such as a keyboard or mouse, but through natural human gestures associated with body, hand, eye, and finger movement. Today our team, consisting of myself, Matt, Jerry, Dean, Darren, Danielle, and Apura, we'll discuss this technology. We'll begin with describing the technology, looking at its value proposition, the state of the current technology, its strategic implications, its technology implications, and finally we'll summarize with some conclusions and a recommendation on why you should invest in this technology. The beauty of GCT is that it's a natural way to communicate. Hand, eye, finger, and body movements are natural forms of communication, and GCT can substitute for what we're used to with keyboards and mouse controls. Software applications are running in the background that interpretate the GCT, and sensors are really the basis of this technology. The beauty of GCT technology is that it runs on sensors connected to any mobile or desktop computer. It doesn't matter. And it could eliminate the need for a computer screen. It can recognize the slightest of gestures and works on many applications in many different industries. It isn't a slow, clumsy technology. Gesture devices will be small and powerful and will allow us to do everything we do today. But it also allows us to do things we cannot do with the devices we do today, which is basically desktop, laptop, and tablet computers. Here are many examples of GCT currently. Some of these you may recognize as the Wii controller in the bottom middle, but others are a little bit more technology cutting edge. For example, we see Pranav taking a picture here. His camera pendant is actually interpreting his hand signal to take a picture. Another one is showing Pranav actually drawing on a computer screen. This is not actually physically touching it, but the actual motion in front. We have manipulating applications with our hands through sensors and signal interpretation for surgery. So how does GCT technology works? There's basically two types of sensors with GCT technology today. First is actual sensors that are monitoring your hand or body movement. The first idea is that natural hand movements can be segmented. These sensors are put onto segments, and then the signals are wirelessly connected to the gesture unit, which is basically a computer running software. Likewise, the gesture unit can project images for us to use. As you can see the picture with the cell phone projected onto the hand, the camera then senses which buttons you've pushed on the phone to dial the phone. This last technology, the camera versus the finger sensors, is rapidly becoming the sensor, if you will, of choice. Arguably, the most critical portion of GCT today is the software. GCT is a very young technology, and it's a work in process which will eventually offer smaller and more convenient devices to wear and to monitor the motion control. Those hardware components, though, are nothing compared to the software that will grow and expand to interpret the gesture control technology itself. Overall, though, GCT must link to other technologies. GCT itself is essentially sensors and software that are interpreting back to a computer as far as what is happening around it. In the past, we've used keyboards and mice, and maybe a couple other control technologies. Today, though, we see the Wii, we see gesture-based control technologies starting to emerge in our car, and we're watching movies about Minority Report that really are pointing towards the future of what motion control or gesture-based controls can really be. One day, gesture-based controlled technology will be job-oriented devices that can be used for specific industrial tasks such as medical, as in surgery, educational, interactive advertising, etc. The sky's the limit. Now that you have a good understanding of the technology, we're going to switch and look at the value proposition. This is very basic and very easy. If you look at a human-computer interaction, we'll call that an HCI, the value proposition for consumers is that we've all been interacting with computers for the last decade, arguably two, on a very archaic basis. The future of HCI is a very natural and easy way to interact with all the computers around us. Instead of worrying about carpal tunnel syndrome in an office, all the interface between the computer and the person will be done very naturally, as our bodies are supposed to move. With 900 million computer users in the world, there's millions of different value propositions and can be very specific to each consumer. The value prop for mobile computing is very simple as well. Let's call this or talk about the sixth sense technologies that is out there. Applications such as maps, drawings, camera usage on a mobile device is utilized much easier with being able to have natural GCT that interfaces with the device. No longer are we typing on a tiny little keyboard or staring at a small screen. It's projected in front of us, and we're using our hand motions to manipulate the map or draw lines from point A to point B. In the world of assisted living, gesture control technology can do everything from controlling wheelchairs to helping the visually impaired by, let's say, giving sensory feedback through vibrations as far as where they're at, and being able to communicate with a computer just by their natural motions instead of having to type on a keyboard or utilize Braille. Rehabilitation is also another key method under the assisted living value proposition, in that computers can naturally understand the movements of the person and vice versa. Sign language also for the deaf is a clear path that will allow computers to understand what somebody is signing to them and vice versa. The values in the medical world is that it's sterile. Doctors and surgeons no longer have to touch various devices. They can actually, through their hand motions, do surgeries, manipulate images, and you can have shortened patient exposure through the anesthesia. The GCT is also a superior to voice control when you're in a quiet room or an operating room. It's easier to control versus yelling or having multiple voices throughout the room. Clearly, GCT has a lot of value in the world around us today. But where is it at, and where are we going with this technology? There's 4 models that we analyzed to assist in determining this. In the following slides, we'll examine the results: the life cycle model, sustaining and disruption model, the landscape model, and the technology S-curve. Our first analysis is on the life cycle model, which was developed by Utterback and Abernathy. This utilizes the evaluation of 12 dimensions to determine which stage of development a product is in, and more importantly, to predict where development is expected to move in the future. The life cycle includes 3 phases: a fluid phase where product development is most active, a transitional phase where process development is most active, and the specific phase where both product and process is declining. As indicated by the red line in the table and graph, our analysis indicates that GTC is approximately 3/4 of the way through the fluid phase. This indicates that a dominant design is expected to emerge soon. The feverish development pace will start to slow, and the competition will decline as the market consolidates. As the product process graph indicates, after the move into the transitional phase, the industry will begin to focus more on product development. In his 97 book, Origins of Order, Christensen develops the sustaining and distribution model. This model is based on the concept that a disruptive technology is one that substitutes for an existing technology by being good enough along the existing metrics of value, but providing superior value along a new dimension. The chart shows a typical situation in which an existing product has areas that are within the range of market demand and areas that exceed the maximum needs of market demand. A disruptive technology has areas that are below the minimum needs of market demand and areas within market demand. When a disruptive technology reaches into the area within market demand, it has the potential to become a substitute for the existing technology. As shown in the chart, the analysis indicates that the existing product features are exceeding the maximum needs. In other words, keyboards and mice have become really good to the point in which they provide minimum needs for a user. Further examination identifies that the market position of GCT is currently below the minimum of market demands. This indicates that the technology has not made sufficient advancements yet to warrant being included as a product that the market will demand. The location of the current market position line indicates that although the product is moving in the right direction, the existing technology is getting ready to be substituted for. The technology is not quite ready to realize the transition. And the technology S-curve model identifies the cradle-to-grave pattern that most products take through the development process. The S-curve is characterized by its flat initial slope, fast rising middle slope, and flat ending. The slopes correspond to different areas of the development process. The initial slope representing the slow beginning that is customary for most products. The middle slope represents the quick pace of technology improvements as a product catches on and becomes popular. The flat end slope represents the end of life as a product as interest wanes and competitive products become more dominant and market shares lost. The analysis of GCT's progress on the S-curve indicates that it is nearing the start of the quick-paced technology improvement phase. The result of the analysis identifies that the market is nearly ready to explode with technology growth as the market comes to a better understanding of the product's capabilities, enhanced product controls, and a higher diffusion rate. And the final analysis is the landscape model. This model utilizes an interdependence value, which is a measure of the complexity of a system. A low K represents a low complexity system, and a high K represents a highly complex system. The analysis of this model identified regards to the hardware, GCT has an intermediate K value, as equipment can be very common and modular across products. This, however, is not true for the complex and difficulty software necessary to run the hardware. Software IP for GCT is categorized as being very complex and requiring specialists to develop the software through nearly every step of the process. The middle graph illustrates the difference in development peaks between the high, intermediate, and low K-type products. And the other two graphs illustrate typical pitfalls for products in the intermediate K and high K scenarios. The intermediate K graphic shows how products may believe they are at the peak, but in reality, a peak with higher potential could be lurking close by, waiting for those with foresight to see the peak and transition over. The high K graphic illustrates that there are many, nearly equal peaks for complex systems. The pitfalls a product can have is that if a product can get to the top of a peak, it then becomes very difficult for other products to make it to the top of the same peak. Having a dual designation of intermediate K for hardware and high K for software allows the confusion that the hardware could peak differently than the software, giving the illustration that a product is dominant, but in reality requires additional growth. The Microsoft Kinect product fits this description in that the hardware uses looks great and is widely accepted by many. However, the software does not allow the system to completely function as demanded by the market, which is the peak. A GCT product that can meet both hardware and software demand specs will likely become the dominant design and will have arrived at peaks for both dimensions. Alright, let's switch gears here and talk about strategy. The 5 dimensions of technology strategy are leadership, scope, depth, licensing and contracting, fit, and timing. These 5 areas will help answer strategic questions about GCT. Let's start with leadership. Companies should assess GCT from an industrial leadership standpoint and determine if it prefers to be the technology leader or follower in the market direction. A company should also identify GCT competencies and align them with its culture, and allow them to leverage it into multiple products. Gesture-based technology firms are mostly prospectors. They will benefit by establishing GCT strategy as their primary focus and allow the firms to become dominant in their field and take market share from the defender. Switching to scope and depth, a company should aim for tight appropriability and new intellectual property. For depth, it could rely on suppliers for much of the value chain and pursue products-based technology innovations. Discussing licensing and contracting, GCT currently has absorptive capacity. The analysis is built to GCT products in-house to ensure tight appropriability by utilizing legal instruments which protect companies' property. And it also ensures that multiple firms cannot easily adopt our technology. Therefore, unless cash flow is prohibitive, in-house development of this technology is recommended. And fit. GCT aligns with the evolution of end-user community. Companies should try to fit the technology into its organization. The technology is currently in line with standard keyboard, mouse, touchscreen technologies, but eventually will become more integrated into other jobs, such as medical, teaching to increase worker efficiency. And finally, timing. The current technology phase for GCT is ready to reap profits and acceptance from technical enthusiasts and visionaries, since it's in the very early market phase. Let's now look at GCT adoption dimensions. Technology strategy is primarily concentrated on factors that have an impact on technology adoption dimensions. The first dimension is relative advantage, which helps us understand the extent a particular technology can provide superior performance or provide enough functionality when compared to current innovations. GCT has relative advantages over computer and laptop, since. Second is observability. This dimension helps identify if the effects and uses of technology are visible. And next is compatibility, which helps us answer how compatible is the technology with user expectations. The fourth dimension is simplicity. It's how simple the technology is. And the fifth is trialability. Trialability helps us make decisions of scale of usage. The table here compares the technology dimensions to technology products. For example, we can observe relative advantages for a computer, laptop, tablet, gaming system, simple and complex gesture control products in one row. GCT provides capabilities that are beyond what others can provide. The data indicates computers occupy the mature phase, and gesture control technology is in the early adopter phase. GCT performance functions that cannot be achieved by computers, but since it is in the emergent technology, it isn't readily observable, has limited compatibilities, and cannot be tested readily due to limited availability. And now let's look at adoption and diffusion. The diffusion of a technology is based off the adoption life cycle. According to this, GCT is in innovator stage due to the development of new products every day in order to define market-driven functionalities. Innovators are attracted to the newness that GCT provides. Sixth Sense technology and the Kinect are examples of gesture products attractive to innovators. Once a dominant design is launched in the marketplace, it is important for GCT to enlist as many early adopters as possible to help diffuse the technology rapidly. Based on the number of early and late adopter stages in life cycle models, we will be able to assess the adoption of GCT in the future. The persuasion of technology is driven by the adoption stage the technology currently resides in. The key areas of technology strategy across the adoption life cycle are early market, which demands a creative technology; bowling alley, which demands a superior technology; tornado demands a sticky technology, which means a technology that can improve upon all adoption dimensions; and Main Street, which demands a service-integrated technology. GCT will reach beyond the early market and go into the bowling alley or tornado phase of the technology life cycle. It will become persuasive in the marketplace and will successfully untether users from computer workstations. As a more integrated and highly personalized technology, we expect many consumer electronics companies will become more involved in GCT startups, and the current clumsy I/O designs or input-output designs will be replaced by streamlined GCT devices, such as finger and camera recognition. Monitors may also be replaced with portable high-resolution projectors that interact with GCT. Concerning the adoption and diffusion discussion, here you can see our slides on adoption phase and persuasion phase. Specifically note the bowling alley and tornado sections and how that's on the rising or the leading edge. Okay, now let's switch gears and move on to the new product development phase. GBC, or let's just say gesture-based computing, is considered a breakthrough technology, although it is complementary and almost incremental to existing technology. Already developed hardware can be assembled together into a GCT system for as little as, let's say, $400. But these are limited in scope and depth and do not generate a lot of enthusiasm from potential investors. The real breakthrough here is through algorithmic innovation that accompanies gesture-based technology, or GCT, that sets it aside from other innovations, making it more than just an incremental technology. It is truly breakthrough. In the new product development process, we have taken the traditional model of new product development and created an iterative process by going from concept almost directly to prototype to not only visualize the technology but also to understand the limitations and disadvantages of using current technology without improving the product through software solutions. This also helped us to understand the risks associated with concurrency and aided in the identification of single points of failure that could affect future R&D projects. Based on the fact that we are expanding on current technology, concurrency was seemingly low risk, and therefore we recommend a fully funded R&D approach. As part of the planning process, when we consider how we are to measure the overall impact of the MPD process, we believe that both cycle time and break-even time are both critical to market penetration and investor opportunities. Creating a plan and executing to what we are calling an accelerated new product development process is aimed at getting the technology out there, which again we believe is key to enticing early adopters. This will help generate the buzz that we want from the technology. We believe that once this happens, the break-even time will be dramatically reduced because this technology will be viewed as cool and sexy in the eyes of the electronic wizards and zealots that thrive on such innovations. So let's get organized. In an effort to make this a very lucrative endeavor to you, with the highest possibility of success, we are proposing the creation of an autonomous team structure for the continued development of gesture-based technology. This structure gives our development team the latitude to accomplish their goals through whatever means necessary and further enhances their creativity in the development of a final product that exceeds expectations. From an organizational perspective, our approach is to centralize our human resources, both in policy and procedures as well as human capital, to leverage intellect, while embracing risk as both a positive and negative attribute to this technology, with combining the best and brightest minds in the fields of computer technology and mathematics. A centralized approach would effectively give us the best advantage of bringing a fully functional, working prototype to potential customers in the very early stages of the MPD process. Through risk aversion processes such as FMEAs and root cause problem-solving tools, we can mend the minds of our resources to create highly competitive and slightly risky attributes to this technology and keep other potential entrepreneurs at bay through these MPD risk mitigation processes. Secondly, our talent will be 100% dedicated to this technology as to never be overextended and ensure timely and accountable milestone achievements. We feel that this technology is an analyzer's dream, an exciting technology for a multitude of industries and products, one that offers a new and exciting technology that has in the past only been seen on movie sets and television, but is now on the coattails of the coming decade. Of course, how do we measure performance? We say this relies on three determinants. If we are to be successful, we must create positive market conditions that will lure potential investors and customers to our technology. This can be done through advertising and networking within our industry. 2, we must ensure that we generate an effective product concept, which we believe this technology has already done. And 3, we must inspect what we expect in reference to the new product development processes, ensuring the MPD process has exemplary performance. This includes MPD cycle time and break-even time. So here we are. You've seen that this is an incredible technology, but you may be asking, so why should I invest? Well, let's just say others like Microsoft and Nintendo are already taking the initiatives, and they've been hugely successful with applying gesture technology to gaming specifically. Windows 8 was also designed to support GCT technology specifically. Definitely the market's heading in this direction already, and it's an indication that large companies feel this is a solid investment. GCT is also a growing market as evidenced by the dollars that we're seeing in touch sensing markets, like the $3.7 billion figure that we will see by 2015. Additionally, gesture recognition devices are going to hit the threshold of about 625 million by 2015. Additionally, there's huge opportunities for GCT because it hasn't even reached the critical mass. While the exception is the gaming industry with the Kinect and the Nintendo, we're still in the very early phases for novel technology, work that's being done in academia and in small labs. There's really no widespread funding except maybe in the operating system world and obviously gaming. And there's applications everywhere in all technologies. And on top of this, other technologies are just too commonplace. Mice and keyboards are everywhere, and the opportunity is huge to replace them. Now is the time to invest. And finally, our recommendations. To begin with, we don't want to pick a specific target industry. We want to develop controls that can be used generically and really not pin ourselves to one specific area. We want to develop multiple computer platforms. It shouldn't be tied to just an Apple or a Mac or even a computer operating system like that. It should be more generic. And of course, we need to develop software libraries. An example of this software library is a sign language to text type of database where we can easily go in and access and control the software to hardware. And finally, maybe more from a hardware standpoint, our recommendation is to build devices utilizing existing components that are out there. Let's not reinvent the wheel, as high-end components are currently a non-differentiator. They really are expensive and they add little value. So we would recommend going out and utilizing existing components. For gesture control technology, this has been Team 1, and thank you.